So we've looked at first order, we've looked at second order, but we haven't looked at applications in the second order yet. And one place to begin that is simple harmonic motion, which is going to be a nice application of the second order. The homework that we're going to do just for today will be these. And then we'll do 15, 18, and 19, and then a together 21 tomorrow. But for right now, I just wanted to start with, if you're looking at these springs, think of a spring just hanging there. That's just going to be my zero, wherever the end of that spring is. As soon as you put a mass on it, it's going to stretch it. They're going to call that S. This is S, the stretch from the spring sitting there to the middle of the mass. Then if you pull it down an additional X, what we'll get will be the total length. We're going to get the length plus X. I like to think of it S plus X, but they're calling the length plus X. And then what we're trying to do is to get this formula having to do with F equals ma. And of course, m is your mass. Second derivative of position is acceleration. There's your F equals ma. So force is going to be equal to the opposite of K times some kind of a stretch. And this is the stretch. S was the stretch with just the weight. X is how much I pulled on it beyond that. So that S plus X is countered by the weight. Okay? And then what they did is they multiplied this out and they said mg minus ks. We're going to extract that out just to look at the force. This is the part that's the balance part, and we'll take that out. Minus kx is what ma is. So when we're done, you're going to get a formula that's d squared x dt squared equal to minus k over m times x. Well, if you move that over, you can see where this comes from. And then if you let omega squared, it's just a symbol, a variable we're going to use to substitute k over m. Then you'll have a second degree differential equation that we'll be able to solve, just like we had d squared x, what did we have? Y squared dx squared, and then we had, I think it was plus, 6y equals 0. Well, this is the same thing except y's are x's. And so what we'll do is we'll see that this is going to be one of those imaginary situations which we'll deal with in a moment. A couple of quick little things here for initial conditions. Initial conditions. What we have here is the position and position and the velocity, original velocity. This alpha, if it's positive, it's going to mean it starts below. So positive is below, negative is above, because it has further to go. And then this one, positive for a speed, means that it's upward if it's positive, and it's downward if it's negative. So you can interpret situations from their initial conditions. All right, so then if we get to m squared plus omega squared equals 0, that's the substitution. M squared equals negative omega squared. And we remember the x of t, or we called it yt before, yc. C1 cosine omega t, C2 sine of omega t. That's the formula we're familiar with. YC equals C1 cosine, we called it beta t plus C2 sine beta t. So we remember that. Two substitutions here, this omega, we can find the period if you go, so the period, really nasty looking t, 2 pi over omega. And you know that because if you had a sine curve and it went to 2 pi, that would be 1 cycle. So if omega was 2 pi, we'd have 1 for your period. And then if it was half that, like that, that means omega would be pi and my period would be 2. 2 cycles in 1 unit of time. Frequency is going to be 1 over that, so you can just take omega over 2 pi. Or more simply put, 1 over the period. Okay. Then we looked at a sample problem. This one here, dt d squared x over dt squared plus 16x equals 0. Initial conditions, it looks like this is below, and this is going to be released from rest. Okay, so then you can, x of t is going to be c1 cosine omega. This is going to be omega squared. So omega is the square root of 16 is 4. So those, what we start with, take the derivative, and then you can find C1 and C2. They found C1 to be, is that 0? C2 is 0? No. X prime of t equals 0. Oh yeah, 4. So C2 is 0, but C1 is just going to be 10, I think. So we have C1 is 10, and C2 we found out to be 0. So that dropped out all the sign, making this your simple curve. Undamped means there's no slowing down of it, and so here's where you'll get the sine and the cosine for that. And then here's where we get the final thing I wanted to show you, and that is we can represent these C1 and C2 on a triangle, and the way that you do that is C1, you have cosine here, sine here. So if you looked at the sine of A plus B, okay, that's the sine of A times the cosine of B, and then it will be plus the cosine of A times the sine of B. So notice that the cosines match, meaning that 2/3, or C1, is the sine of A. C1 is the sine of A. And then for this one, C2 is the cosine of A. So when I make a triangle, beta, if these are over 1, okay, you're going to have C1 over, well, actually not over 1, it's over something here, and cosine C2 is going to be over that. So it's all because of the CC. Sine is first, making cosine across from phi. We're going to call this phi. Okay, so now, finishing this, we use Pythagorean theorem. We're going to get the amplitude A, square root of C1 squared plus C2 squared. Now, for phi, that's going to be the inverse tangent of opposite C1 over C2, not C2 over C1. And then once you have those, you can put that into this formula. A is c1 squared plus c2 squared, or c1 squared, c2 squared, square root. Omega is from the problem, and then phi is the inverse tangent of c1 over c2. And that finishes off the basics here. So number one, you're reading and interpreting these. Remember, negative of the position is going to be above. Negative in the original speed means upward. Okay. K is here. This is going to be your weight. And 32, apparently folks don't know that. G is 32 feet per second squared. That's an acceleration. And then for 3, 5, 7, you just find that equation and then convert to x equal to a sine omega t minus phi. You're going to convert it to that formula. Good luck.